My name is Manuel Serrano. As you can probably guess from my accent, I'm coming from France, where I'm a researcher at INRIA, which is a French research institute in computer science. So since a couple of years, I've been working on JavaScript, and in particular in trying to implement and design a static compiler for this language. And this is what I will present today. So I will start slowly, not assuming that you know all the details and all the subtleties that come with this language. So I will try to make a smooth introduction, and then I will present some of the results we have obtained. So JavaScript, and you see the title, A Nightmare for Compilers, and I will try to show you why. Most of the things I will present in this introduction are well known, but still I may assume that some of you are not so familiar with all these subtleties. So let me start with this example, and for a while, let's assume that we are a C or a Java programmer. Even if you are not exactly familiar with all technique of compilers are deploying and all the optimization, you may have a rather precise idea of the code you will get if you will try to compile this with, let's say, GCC-02. Probably you know that you will get something like that, because you know that A and I will be registers, you know that the loop will just be incrementing a register, comparing something, reading from a contiguous memory area, and just jumping for the loop. So far, so good. So now let's assume that we are no longer a C programmer, but let's assume that we are JavaScript programmer. The story looks like the same, because the syntax is the same, but what is going on actually? Well, it all depends. Because if A is an array, as before, the semantics of the program is exactly the same as the semantics of a Java program. But the problem with JavaScript is that A might be something else. And in particular, A might be an array, but you can remove properties from an array, and you can store property in the prototype chain of that array. And then when you are executing the loop, when you reach A of 1, you no longer find the value in the array itself, but you have to follow the prototype chain. So you see in the C code, you were just reading from a contiguous memory area. In this code, it's no longer that same story because you have to follow the prototype chain. So the code that you will generate will obviously be much more complicated. But things can be even worse because A might be something else than an array. A might be an object. And this is perfectly fine as long as this object has property named after the integer we were using for the array. And this is correct because the JavaScript semantics tells you that when you are accessing something from an object, you first convert the property into a string, and you make a lookup in something like a hash table. So this program is perfectly fine. And you see, I have paid attention not to have contiguous object properties here because I go from 1, 0, and 2. So really forget about this idea of reading from a contiguous memory area. It will be a totally different matter. But I can do even worse, because if I change slightly my program, and if I replace I++ with I plus equal 1, you know in JavaScript, I++ and I plus equal 1 are not the same. If I do that, I might even be something else than an integer. It might be a string. And then in that context, I will concatenate things in my string and making an index from that value. So you see, the idea we had with C, where it was pretty obvious that the implementation of a loop was just a bunch of assembly instruction, clearly with JavaScript, forget about that. It will be a totally different story, totally different problem for the compiler. And the difficulty here we have is that the syntax of the language tells us very little things, and so does not provide significant help to the compiler. Let me keep digging a little bit more deeply into the specificities of JavaScript. If we have this piece of code, it's pretty obvious how GCC will compile that. Basically, it will generate that. Accessing a value from one pointer is just one assembly instruction, pretty obvious, pretty straightforward. You don't even need to have a smart compiler for generating that. What about JavaScript? Well, same syntax as Java, but the story is now radically different. And here you see excerpt of the specification of the language. So if you want to execute O.P, you have to follow these semantic steps. And the first thing you notice is that in this semantic function, you have several steps to execute, several tests, several conditions to verify, several bench that you have to take depending on the value you get. But the thing that is even more complex is that you see at the very first line here, The first thing that the semantics tells us is that if you want to get the property, well, you have to invoke another semantic function even before doing this dispatch which is over there. What is this other semantic function that you have to execute? Well, this is the one that will tell you how you have to follow the prototype chain. So this is actually implementing a loop. You check, do I have my property in that object? Yes or no? If it is there, I will return it to the other function that will make the testing. Otherwise, I will follow the prototype chain. But you see here, this function, it is using another function here. So what is this other function? Well, this is the one. So this one tells you that, yes, make the lookup in the hash table. And if you find the value, you see there is this weird syntax somewhere around here, which is allocate. Allocate an object and return that object. That is, when you are accessing a property from an object, the semantics tells you that first you have to make some heap allocation. And of course, the compiler will be able to somehow not execute all these steps. But once again, remember, in C, accessing a property was just one assembly instruction. Here, you imagine all the paths that we have to follow in order to make the efficient property access. So mitigation for that problem have been discovered a while in the past, and they are used in all JavaScript implementation. They get rid of most of these steps, but still, we are pretty far away from the performance of C when accessing an object. Maybe the last example I would like to show you today, function call. Here we have a C code where we have an external function f, and we invoke it with two arguments, 1 and 2. We get the result, and we sum it with 3. Okay, in C, pretty simple. You just pack your argument in the stack. If you are using an x86 platform here, you just push the argument on the stack, you make the call, you get back the result, you add 3, you return, you're done. Pretty simple, pretty straightforward. What happened with JavaScript? Well, JavaScript is dynamically typed. So the first thing that you have to verify is f really a function? Am I allowed to call f? If I'm not, I have to throw an exception. So exceptions are involved here. Let's assume that f is a function. Next thing you have to verify is f a function accepting 2 arguments? Because it might be that f just accepts 1 or 0 argument. And in that case, you will have to drop the extra arguments that you are passing to the call. On the contrary, it might be that f is expecting more than 2 arguments, and then you will have to complement the missing arguments. When I say you will have to, it means that the runtime system will have to. So it means that you will have to do something at runtime. If f happens to be using this special value, arguments with an s, it means that you will have to heap allocate a value representing all the arguments that you are passing to this function, and you will have to deliver that value, which has a dynamic extent, to the function, which will be able to use it as it wish. Then you will have to assign the zeros value, and then eventually you will make the call. So you see, once again, we have the simplicity of C, which is just pushing something into the stack or in register, depending on your platform, while with JavaScript, totally different story. And once again, the problem is that the structure of the program does not really help the compiler. The syntax tells us does not provide sufficient information so that we are able to implement that efficiently. Okay, so ahead of time compilation of this crazy language. Because I'm not assuming that all of you are exactly and precisely familiar with all the technique we are using when we are implementing a compiler, a very brief introduction of how we are usually implementing programming languages. On the very left part, you have interpreter. And typically, this is what you find for Python. The CPython implementation is just an interpreter. Interpreters are used for fast development cycle because you execute as you go with your program. You read the program, you execute. So it's very convenient for making some experiment. Fast development cycle, as I said. But the downside is that you have very slow execution. At the very right part of my drawing, you have ahead of time compiler, static compiler, which a couple of years ago were just called compilers. Today we have to say AOT compilers. Typically, this is what you get for languages such as OCaml, GCC, Rust, all these kind of languages. Slow development cycle, because usually compiling statically one of these programs takes a while. If you have a large C code and you try GCC-03, you will notice that it takes a while. Complex implementation, because developing such compiler is a complex task. But the good side is that it delivers good performances for static languages. In the middle, you have things that are just a little bit of interpreter, a little bit of static compiler. You have typically bytecode compiler, such as the Java-C compiler. Here, the purpose of the bytecode compiler is to simplify a little bit the execution by implementing some operations, such as, for instance, resolving variable names, maybe preparing the construction of the execution stack, but nothing too fancy and nothing too complicated. And then you have JIT compilers, and JIT compilers are typically PyPy or what you get in all the commercial JavaScript implementation. JIT compilers allows fast development cycle because as a user you do not even notice that the compiler is existing. You just run and you just start your program and it runs and the JIT handles everything for you. It's super complex implementation because you have to implement an interpreter, a compiler, and something that is able to replace the code that you are interpreting with the code that you will get generated by the compiler. So it's really extra complexity. And it's quite convenient for dynamic languages, in particular because the JIT compiler is able to do some profiling, so discovering during the execution what is going on and what is the best code it can generate. What we are trying is we are trying to build this hop compiler, which is a static compiler for JavaScript that is not taking the same approach as JIT compiler. So this compiler exists, it's called hop.js. It's an opportunistic compiler, and you will see what I mean by that later on. It supports full-fledged JavaScript. It is almost compliant with the latest version of JavaScript. It is also almost compliant with Node.js, which means that you could potentially use this compiler as a replacement for Node.js. But it optimizes the core language, but there are some parts of the language that it does not optimize yet. So it means that for this part, you will not get good performances. And typically, some library functions are not well optimized, or some data structures are not well optimized neither, such as floating point numbers that the compiler does not optimize so far. So the first question is, does it really make sense to try to compile statically a language such as JavaScript? Well, the motivation for this work are numerous. The first one is that on some platforms, you are not allowed to write the executable memory. So for these platforms, you cannot rely on a JIT compiler. Typically, if you want to build your own JavaScript implementation for iOS, for instance, you are not allowed to change the executable memory, so you cannot do it. Forget about it. So you have either to use an interpreter or a static compiler. Then you have platforms which have very limited memory. Platforms such as microcontroller, for which you cannot consider embedding a JIT compiler in the platform because the memory is not enough. Then you have executions that are very short, typically cloud services, or even imagine, for instance, a shell command. Imagine that you want to implement ls in JavaScript. Maybe just running ls is too fast, too quick, so the JIT compiler will not even have the time to optimize ls before the execution has completed. So for this kind of execution, a static compiler might help. And also, as a researcher, this is an intriguing question, because all the current implementation, all the currently fast implementation are using JIT compiler, but does it mean that it is not possible to build a static compiler for such a language? Or how far can we go in this attempt of building an optimizing ahead-of-time compiler for JavaScript? So all of these are a little bit of my motivations. So the question then, the second question is how to attack the problem, which seems difficult. Well, first of all, we will accommodate the technique of JIT compiler to static compilation, and I will show you more precisely what it means. Then we will reuse all the things we know about compilers and all the things we know about optimization. That is, we will do a little bit of typing, we will do a little bit of data flow analysis, a little bit of control flow analysis, and what we will do is a lot of optimistic heuristic, and this is the point that I will develop in the rest of this presentation. So, optimistic compilation. The idea is pretty simple, pretty straightforward. Consider a function such as this one, the Fibonacci function. Well, the idea is just we will generate several versions for such a function. One version specialized and optimized for a dedicated type, and a generic version. And we will just make a dispatch, selecting according to the type which version to select. And if we are happy enough that the arguments are of the optimized time, we branch to the efficient version, and we are done. So why is that significantly better? Because in the optimized version, we will be able to use dedicated operators that are not strictly following the JavaScript semantics, but that are much more efficient. And also, because using the type inference, we will be able, for instance, here and there, on the recursive call, not to go through the dispatch, but directly branching to the optimized version. So the idea is pretty simple, and more or less, it's doing statically what a JIT compiler will do, selecting the proper type and generating several versions. So the question is, how do we select the type for which we want to generate this version? And here, the idea is absolutely straightforward. In the past, when we were doing type inference, we were always trying to find the most generic type representing all possible execution. In this context, we are not interested at all by these types. The only types we are interested in are the types for which a compiler is able to generate a good code. So instead of trying to infer the most general type, we will just try to find out which is the type for which a compiler is able to generate its best code, and this is the type we will select. This is the type we will pick. And for the rest, we don't care. So how does it work? It's extremely straightforward. We walk through the program, and for each expression, we apply a rule. And the rule tells us, for this variable used in this expression, if it was of that type, I will be able to generate a good code or a bad code. And we just, for each expression, we apply all possible rules that we have, and at the end of the day, we just check what has been produced by the rule, and we select the most efficient type. So what are these rules looking like? They are of this kind. We say, when you have a property access from an object X, a property E, if X was an object, then we will be able to generate a better code because we would be able to avoid a type check. If in addition, we knew that E was an integer, if X was an array, we would even be able to generate a better code because we have dedicated operation for accessing arrays with integers. If the property happens to be length, then if the value was an array or a string, we would be able to generate an even better code because we have dedicated cases for these two special cases. If we see an assignment, as strings are read-only, we know that we can forget about strings, so this is why we use this minus infinity type here, weight here, saying that we are not interested in having X being an array, string, sorry, but we are interested in having X being an array. And we keep going with all these rules. We have plenty of them. I just presented a bunch of them, but we have much more. We see we have rules of this kind where we say, if this is a bitwise operation, if the object happens to be an integer, then we will be able to generate good code. Otherwise, we'll have to go through a dispatch, so we are not interested in other cases. So let me show you on an example how this works. Let's consider this function that is just reversing an array of values. And we just apply the rule blindly one after the other. We have an expression of this kind in the program, A of length. So by applying rule 1, we say, OK, A, please the compiler, make it an object. But by applying rule 2, we also have dedicated rules for array and for strings. We have an access of this kind. So by rule 1, we increment the object type for this variable A. The type inference tells us that I is an integer, so we increase the weight of array and string for the possible type for A, and we keep going like that. And at the end, we observe that, OK, the best possible type is A being an array. And you see that absolutely simple because it's just one pass. You just accumulate the weights, and at the end, you just pick the most probable or the most optimizable one. And then, when you are done with this type, you just generate the code as I have presented before. You have your dispatch, your dedicated function, the generic one, and on the two possible calls, either you are able to branch directly to the optimized version, or you go through the generic version, and that's it. And this is how we implement this sort of opportunistic compilation. We have just generated the best possible code, and we have made a bet in some sense. We have guessed that this was the code that is likely to be used. This is one of the things we have in the compiler, but this is not it. JavaScript is a very big language. core language is complex because you have all these prototype things, you have inheritance which is complicated, the language keeps growing, you have extended set of libraries. So for a very small academic team, it's not really possible to implement efficiently all this aspect of JavaScript. So what we did, instead of considering JavaScript and generating native code, we consider JavaScript and we generate Scheme code. So this may seem a little bit weird, but actually Scheme is the original motivation for JavaScript. So Scheme is actually very close to JavaScript, except that Scheme is much more simpler and it has a cleaner semantics. Many of the dynamic aspects which are very complicated to deal with JavaScript are absent from Scheme. So Scheme can be considered as an interesting intermediate language for JavaScript. So we have been doing that, and we reuse a Scheme compiler that generates C code. So actually the full compilation chain is we go from JavaScript to Scheme, Scheme to C, and C to assembly code or object code. Okay, now let me show you just another example of this idea of opportunistic compilation when Scheme is involved. So if you are not familiar with Scheme, don't be too afraid with this piece of code. I will show you the very same one in JavaScript in just the next slide. But still, here we are defining a function called getCtor, which will return a function, ctor, which is defined here. This creates an object, and the only interesting part here is that function uses two free variables, CNT and base, and this one is a floating point, this one is an integer. This is the only part which is interesting, and here you see we are assigning a new value to CNT, which means that we are mutating this free variable. Okay, oops, sorry, my arrow is a little bit weird. How is that implemented, or what is happening at runtime when we are executing this piece of code? Well, here you see this is the assembly code for this function over there. This is the value of the floating point. This is the value for the CNT variable. And this is the object representing this function, this ctor function in memory. This is very classical. This is a standard way of compiling Scheme. A function, which is a data structure, contains its free variable. So this is a heap allocated structure. Okay, enough for Scheme. So now the very same thing in JavaScript. Exactly the same program, exactly the same meaning. I have my ctor function. I return the ctor function. I have two variables, free in this function, and I assign CNT. So exactly the same program. What is the difference with JavaScript? Well, in JavaScript, you need this extra memory and this extra object, because in JavaScript, a function is a regular object, so you can assign properties, or you can store values arbitrarily as you want in your function. So you see in Scheme, we had just this object, and in JavaScript, we have the overhead, which is all this new object that has appeared. So clearly, you can see that JavaScript will not be as efficient as Scheme by no means. But what do we do with that? Well, the idea is that, okay, in the general case, a JavaScript function or a JavaScript closure will be an heavyweight object, but in many cases, we know what we will be doing with the function. And in particular, for this kind of cases, which are extremely frequent, you are just invoking the for each function on an array, and you are passing here an arrow function. So the idea is that it would be a shame to allocate a full-fledged JavaScript function for this arrow function, because we are just invoking the JavaScript library function for each, which is not doing anything special with that function except calling it. So the way we compile that is we generate this Scheme code. That is, we are assuming that for each is actually the for each of the array library of JavaScript. And then, instead of building a true JavaScript function, we just allocate on the stack a Scheme function, a lightweight Scheme function. And this function here, and we call so this function JS array maybe for each. And how is this function implemented? It just checks, is the receiver a regular array that is not overriding for each? And if it is, which is always, it just directly invokes that function without allocating anything. And if it is not, then it goes through the slow path. So we are somehow making a bet here. We are guessing that, yes, the user is not overriding for each of arrays, and yes, he is using for each with arrays. And if he is, then we have a very efficient code. as efficient as the scheme code. And if it is not, then yes, we will follow the slow path. So this is another example of how we are using this idea of opportunistic or optimistic compilation in a static context. Good. So what about performances? When you are dealing with JavaScript and JavaScript efficiency, it is impossible to get any paper accepted if you are not presenting official JavaScript benchmarks. So you have to go through this Jetstream, Octane, you name it. Although these benchmarks are known to be flawed, to have biases that you don't want to deal with, but still you have to present these values. So here we are for Hop compared to V8 and SpiderMonkey and the other player. So Hop is in yellow, and you see that in this test suite, it seems to perform not so well. But actually, there are reasons for that. First, as I mentioned before, Hop is not optimizing floating point numbers. So all the benchmarks that are using floating point numbers have poor performances with Hop. And then you have other benchmarks for which there are special patterns. And if you miss these patterns, then your performance are awful. And Hop is not able to optimize all of them. Some because we don't know how to optimize them, and some because we simply don't care. And I will show you two examples of these patterns. Let's consider del tableau here. In the code, you see this pattern. This direction is just actually the implementation of an enum, but it is used as an object everywhere. So if the compiler is not able to detect that this is a constant, this is an allocated object, that is never used as an object, only assigned here, and make a replacement, that is a constant propagation here, the type inference is not able to do a good job and your performance will be doomed. Hopefully, for this very case, Hop is able to optimize that, but there are other cases slightly similar to this where Hop is not able to do a good job. Let me show you another example, my favorite one. It's an example, so crypto SHA-1, as you know, as you can imagine, it's a function implementing a crypto function used in a crypto library. And in this code, you see this function. And you see it's an interesting one because what it does is it creates an array. And here in a loop, it executes this bit OR operation. But you can notice that array bin has not been initialized before. So actually this code is totally broken because if someone assigns something in the array.prototype object, your crypto library will be totally corrupt. So this code makes no sense at all. So yes, Hop is not able to optimize that, and it has poor performance on that benchmark, but really, is that a problem? We are not optimizing this wrong code. And you have this kind of problem in many of these Octane, Jetstream, and so on. So what we did is we designed another test suite for which we got our program from different sources. We took program coming directly from NPM packages that have no dependencies. We use this program in our test suite. We ported some program from other languages, and typically from Python and from Scheme. And so we designed a large set of new benchmarks. I presented just some of them here. And you see, because we are interested in comparing JIT performance and ahead-of-time compiler performance, it's not a peak performance that we are interested in, but we are also interested in understanding how the performance evolves if the complexity of the problem evolves. So here, in the horizontal axis, you see the program is getting more, the data set, the input of the program is becoming more complex, and so the execution lasts longer. And you see how the comparison in between the different implementation evolve over the time, depending on the complexity of the problem. So you see for this program, Hop performs similarly to other JIT compiler. So here, BASIC, it's a basic interpreter. Marked, it's a Markdown compiler. Sorry, I have to grab my glasses. Level, it's a scheme interpreter. And BAG is just the implementation of a small game using recursive function and integer manipulation. Just to keep going with some other example, Moment, it is the most popular package on NPM, and it's a package dealing with dates. And the runtime implementation of date in hop is not so great. We are not very good at implementing date function, so it is not performing so well, but it's just twice slower than SpiderMonkey, for instance. So it's not that good, but it's not that powerful either. Here it's a program parsing the command line, and this one checking computing unique identifiers. This program is interesting. It's a version of the recharge program from Octane, but where we have introduced proxy object each time we create a value. And you see that outperform all the other implementation. And we know why, because we have a special optimization for proxy. But the interesting point here is that even for a very dynamic feature, in a static context, we are able to deliver good performance. So that's it for execution. The promise of having a more efficient memory consumption, here you can observe it, that yes, indeed, hop is really provide better performance when we are talking about memory, because you don't have to embed the JIT compiler in your heap when you are running your program, and we observe that for the virtual size and the resident size. And I think I'm done. So just in conclusion, we have built this static compiler. It fully supports JavaScript. It uses a lot of optimistic and opportunistic techniques, and these are described in the paper we are publishing. It is not as good as the most efficient JIT compiler yet, but it delivers competitive performance. That is, most of the time, we are in a range where we are as fast or 2 or 2.5 times slower than JIT compiler, but nothing worse. But in terms of memory footprint, we are much more efficient because we are not embedding the compiler. And I thank you for your attention. And I don't know if we have time for questions. No, we don't. No, I think what you are referring to is profile-guided optimizations. JIT compiler, I don't know, because it requires an infrastructure and the hop runtime system is not ready for that. Profile-guided optimization, yes, definitely yes, and hop is doing a little bit of that. But I did not mention that in this presentation because so far the results I have obtained are slightly disappointing, because with profile-guided optimization, more or less we are able to reduce the generated code size, but we are not accelerating execution. And my guess for that, it's because with profile-guided optimization, maybe you can remove some of the guards that you have or your dispatch, but these generally are optimized by the processor and by the branch predictor of the processor. So there is something that I don't really understand here, but yeah, this should be interesting, but not so far. So no, we don't have the whole program because it compiles modules. So inside the module, yes, we are able to do some global analysis. And yes, I think we are able to do a better type analysis, in particular because we are using abstract interpretation for executing everything. But in the end, a JIT that is able to do some precise profiling will also probably be able to discover the types that we are discovering. So it's not so clear that it is a huge advantage. Maybe, but maybe not. The next step, I think, for me is rather to try to reuse the types that are generated by the TypeScript compiler, because this is a different settings and probably more friendly to static compilation. So this is the next thing I will experiment with. I don't really know. With these languages, JavaScript or maybe Python, there is this performance cliff phenomenon. I don't know if you are familiar with that. The idea is that as long as you are in a subset where the compiler is able to understand what you are doing, you have good performance. But if you change it a slightly bit somewhere, all of a sudden, maybe your performance will degrade with a 1000x ratio for a reason that you as a programmer cannot understand. For hop, I'm experimenting something slightly different. In JavaScript, you have this different mode. You have use strict, and in the past, Google has tried, what was the name, use strong or something like that, which was even stricter than use strict. And for hop, I'm using something similar. I have a dedicated mode where some of the JavaScript features are removed or not allowed. And then if you use this mode, syntactically it's JavaScript, the data structure are compatible with JavaScript, but there are some operations that you are not allowed to execute, and then you are guaranteed to have better performance. But you are sacrificing a little bit of the dynamicity of the language. But this is compatible with the rest. So some of your module might be in that mode, and the other modules in regular JavaScript mode, and you combine that, and that's okay. So this is the approach I'm following. Yeah? I don't know. In theory, I could say, yes, I will spend time, and I will succeed in optimizing that. I don't know. Maybe there are difficulties that I'm not even suspecting. Honestly, I cannot answer that question. I'm not even sure that this is doable, to be totally honest. I think so, but I cannot guarantee that. Okay. Thank you very much. Thank you for your attention.